Okay, so we're going to show that differentiability implies continuity. So this is a theorem, and it says that if, so the hypothesis of the theorem is if the function has a derivative at a, and then the conclusion is that then the function is continuous at a. So if I assume that the derivative exists, then I know that the function is continuous. So having a derivative is stronger than being continuous. It implies that the function is continuous. So I'm going to prove this for you, but first let me give you intuition why this should be true. So this, if you think about it, this statement is exactly the same as the statement that if the function is not continuous, then it's not differentiable. So being differentiable implies continuous is exactly the same statement as saying not being continuous implies not being differentiable. And so let me sort of give you intuition for why this one should be true. If I have a function that's not continuous, so we sort of know a few ways that a function could not be continuous, right? If there's sort of a removable discontinuity, if there's a jump discontinuity, if there's a vertical asymptote, say something like this, or if, let's say if the point is not even in the domain of the function, so let's say my function looks like this and I'm asking about something happening over here, then these are sort of 4 ways that the function could fail to be continuous. And in all of these, if I ask, what is the slope of the tangent line at this point, it's not clear what I mean. I mean, if I draw a tangent line here, I could draw a line with any slope going through where the function is defined at this point, right? Any slope, and it would make equal amounts of sense. So the slope of the tangent line here is not well defined. Same thing here, like if I'm asking about the slope of the tangent line here, it's not clear what I mean. Like, should I draw a line like this? Should I draw a line like this? Should I draw a line like this? We don't know. At this point, if there's a vertical asymptote, the slope of the tangent line sort of, it would have to be like the tangent line. Maybe you could think of it as vertical. And in that case, the slope, a vertical line doesn't have a well-defined slope, right? And then same thing here, like if the function's not even defined, then I definitely can't draw a tangent line to it. And so if I can't draw a tangent line to this function, then this means the derivative is not well defined. So this is sort of the intuition. Let me prove this for you. So let's just show, my goal here is to show that the limit as x approaches a of f of x is equal to f of a. So this is what I'm going to show. This means this is the definition of f of x is continuous. US at x equals a. Right, that's the definition of continuity. So if I can show this, then I've shown that the function is continuous at a. So let's show this. I'm going to assume that f of x is differentiable at x equals a. So the derivative exists, and then I'm going to show this statement. Okay, so how am I going to do it? I'm going to notice that if I look at this difference quotient, f of x minus f of a over x minus a, and if I multiply this thing by x minus a, then these things cancel unless x equals a, right? So if what I'm saying is that if I just write f of x minus f of a on the left-hand side, and I look at the right-hand side, these two functions are the same function, except when x equals a, right? When x equals a, this side is not defined. And when x equals a, this side is defined, it's 0. But besides that, every other point, these two are the same functions, right? And so since they're the same function everywhere except at x equals a, I can take the limit of both sides. So this is the limit as x approaches a, limit as x approaches a. And now I can evaluate this using the rules of limits. So this is the product of two functions, right? It's the product of x minus a and this difference quotient. And if both of these limits exist individually, then I can take the limits individually and multiply them. So I'm saying that this is equal to the limit as x goes to a of x minus a times the limit as x goes to a of f of x minus f of a over x minus a. This is true if both of these limits exist. And now I claim that both of these limits do exist. This one just goes to 0. As x goes to a, x minus a goes to 0. So that's 0, that's good. And this one, this is the definition of the derivative at a, right? X is going to a. This is the difference quotient between x and a. So I'm taking the secant line between these 2 points, x and a, and squeezing them together. And so this, by assumption, this exists. This is the derivative. So it's 0 times this number, f prime of a. So f prime of a is just some number. It's the slope at that point. And so what I'm saying is the limit of f of x minus f of a is equal to 0. 0 times whatever number this is 0, right? So this limit is equal to 0. And now if I just rearrange this, this is a constant, right? So I'm going to move this to the other side. I'm going to add f of a to both sides here. And what I get is exactly this statement. And so this shows that f of x is continuous at a.